Right, you lot, I'm going to try and do Dr. Patel's questions for you. No, I haven't done this side of the course for a while, so bear with me. It might be a bit slow. So anyway, here are 3 amino acids shown below. The way I remember amino acids, by the way, all amino acids have this pattern NCC, NCC, NCC. So if you've got a load of amino acids joined together, in other words, a protein, it will always have this pattern NCC, NCC. There'll be an amino there, and an acid there, an amino there, an amine here, and an acid there. And it's the thing that's joined to this central group that determines what the amino acid is. So if you notice here it goes NCC, 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 amino acid. And this bit in the middle is changing. Anyway, draw the Zwitter ion of alanine. Well, there's alanine. So what can happen to these at their isoelectric point? An H plus can come off this end and go on to this end because this end's got a lone pair. This is an acid. So the H plus drops off the acid and it can go onto this side. So the Zwitter ion of alanine is you draw your NCC, you got your double bond O minus, and this is NH3 plus. Everything else has to stay the same. That's a piece of cake. Zwitter is from the German meaning a bit of both, like both I think it might mean. Zwitter. So it's both positive and a negative ion. So that's the Zwitter ion. Overall it's neutral because it's got a positive ion and a negative ion. So anyway, draw the species that is formed when valine is dissolved in an alkaline solution. So what an alkaline solution will do, alkali is OH minus, it will remove H pluses from valine. So what I'm going to do, I'm just going to draw valine, NCC, you're going to learn that from this video. There's valine, CH3 twice, that bit doesn't change. In alkali, so there's valine, in alkali, that H plus disappears. So the alkaline version of valine is that, O minus. Draw the species formed by lysine at low pH. Low pH means in acid, so when there's H plus around. So you do NCC, NCC, put your H on and your group, which you can't be bothered drawing. At low pH then, that means when there's loads of H pluses around. Well, if there's loads of H pluses around, that means this H is definitely still going to be stuck on. And this end will pick up another H plus by virtue of its lone pair there, so you get this. So at low pH, you form this. So at high pH, in alkaline conditions, you form negative ions, and in acid conditions, you form the positive ions. Draw the two dipeptides formed by the reaction of alanine with valine. Well, what you can have, biologists will know this, you can either have ala joined with valine, like this way round, or you can have valine joined with ala, but it wants more than this. So anyway, if you're drawing a dipeptide, do this, NCC, NCC, and it wants 2 of them, so you go NCC, NCC. This does make things easier. I am quite a good teacher of things like this. So on these ones, there's a double bond O, because that's from the carboxylic acid. NCC, NCC. This will have, at this end of the carboxylic acid, you'll have the acid bit. At this end, you'll have the amine bit. At this end, you'll have the amine bit. At this end, you'll have the carboxylic acid bit. Then you finish off the other nitrogen with an H, the other nitrogen with an H, and you put an H there, an H there, an H there, and an H there. So they're all the same. Those bits are the same. All I've got to do now is put the right thing there, the right thing there, the right thing there, and the right thing there in that last bond space. So what you would do, if you're going to do ala and then val, you'd put CH3 here, and then valine is CH3, and this would be CH3, and CH3. NCC, 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 NCC. Alright, name a suitable method by which the mixture of amino acids formed can be separated. The best way to separate amino acids is thin layer chromatography or just any sort of chromatography. So it's after chromatography. NCC, NCC. When two aminoids, oh no, second page. The structures of the amino acids alanine and glycine are shown below. Give the systematic name for alanine. Ooh, right. So, what you've got here then, when you're naming one of these, you name the longest chain first, even though it's called alanine. There's 1, 2, 3 carbons. It's a that is there propanoic acid. Propanoic acid. And in position in carbon number 2, there's carbon number 1, there's carbon number 2. You've got an amino group, so it's 2-amino propanoic acid. Alanine exists as a pair of stereoisomers. Explain the meaning of the term stereoisomers. So that's same structural formula, but arranged differently in space. Same structural formula, but arranged differently in space, or atoms arranged differently in space. States how you could distinguish between stereoisomers. So alanine has got a chiral carbon here with 4 different groups attached. They would rotate the plane of polarized light in different directions. So I assume you've done optical isomers. I think you have. They would rotate the plane of polarized light. They would rotate the plane of polarized light. They would rotate plane polarized light. They would rotate plane polarized light in opposite directions. Right, give the structural formula of the species formed by glycine at pH 14. pH 14 is alkali. So you're dealing with glycine. So I'll draw glycine, NCC, double bond O, H, glycine, H there. And you've got to decide, well, there's just glycine. Think what will happen if you put OH minuses into this? Well, this hydrogen will drop off and you'll be left with that. It's easy, that, Mark, by the way. You've got to just realise it's easy, I suppose. When 2 amino acids react together, a dipeptide is formed. Give the structural formula of the 2 dipeptides formed and alanine and glycine react together. NCC, NCC, dipeptide, 2 peptides. NCC, NCC. Let's get all the easy. Make sure we get the acid on one end, amine on the other. Double bond O there, double bond O there. H here, H here, H here, H here. Now all you've got to H here, H here. Now all you've got to do is put different groups in those positions. Alanine, do the one for alanine and gly, whatever that side group is, gly and ala. Give the structural formula of the organic compound form when glycine reacts with methanol in the presence of a small amount of concentrated sulfuric acid. Now again, I'm not sure if you know this yet. It depends if you've done it yet, done it. Let's have a little look. Sulfuric. Anyway, I'll do it. What question am I on? I need to draw glycine. Glycine is this, NC. It's esterification. I'm not sure if you've done esterification. When I see sulfuric acid and adding an alcohol, you're adding an alcohol to a carboxylic acid group. So there's glycine. If you add methanol to this, which is that molecule, what happens is water is kicked out and you end up with NCC, double bond O, O, CH3. It's called an ester. I don't know if you've done esters yet. But anyway, that's what forms. Question 2. Next question, question 3. You know what? I'm not sure if you've done this yet either. Polyamide. By considering the functional group formed during polymerization, name this type of polymer. Well, what you've got an amide group there, and you've got another amide group here, another amide group there. It's called a polyamide. I'm not sure if you've done them. Oops. And when these form, it's a condensation polymer. So this will be fine for you if you know it, but it's a condensation polymer because every time these join together, they kick out water. Not sure if you've done it yet. Draw the structure of the species present in solid amino ethanoic acid. In solid amino ethanoic acid. Give the structure of the amino ethanoic acid. in solid aminoethanoic acid. Well, I've drawn that. I can only assume they mean the zwitterion. Is there something I'm meant to know? Solid amino. When it's a zwitterion, it'll be an ionic compound, which makes it solid. Let's have a look at the mark scheme. Yeah, they wanted the zwitterion. I'm not sure why they wanted the zwitterion. I'm missing the point of that question. Explain why the melting point of aminoethanoic acid is much higher than that of hydroxyethanoic acid. All right, because this will have ionic bonding. You'll have another NCC over here with its negative charge and its positive charge. You'll make a giant ionic lattice. This zwitterion will have ionic bonding. This one will bond to its neighbour by strong electrostatic attractions, whereas this will only have hydrogen bonding between neighbouring molecules. Alright, question 4, cisplatin. I don't think I asked you to do question 4, so I'm moving on. Question 5. The amide or peptide link is found in synthetic polyamides. Synthetic means man-made, and also naturally occurring proteins. Draw the repeating unit of the polyamide formed by the reaction of propane dioic acid with hexane 1,6-diamine. Oh, I've set you up with some right stinkers here. These aren't even protein questions. Oh, I just set it too quick. Right. Have you done polyamides yet? Do I do this? Or... Right, I'm going to miss this one out because it's not to do with proteins. Sorry everybody if you got stuck on that. Again, same thing here. I thought this was all proteins questions. I've let myself down, I've let you down, I've let Dr. Patel down. Alright, let's have a look at the dipeptide question. The dipeptide shown below is formed from 2 different amino acids. Look and go NCC, NCC. Draw the structure of the... Actually, that one there is that carbon. There's the M acid. Amine acid. Amine bump acid. They bent it round to make it a little bit tricky for you. Anyway, the alternative dipeptide that could be formed, so dipeptide is NCC, NCC. I'll put a double bond O, OH on this end. I'll put a double bond O there. I'll go H, H. So NCC. So I want to put this amino acid on this end. So I'm just going to go H, H, CH3. And all I've got to do now is transpose this amino acid into this position. So this central carbon has got an H on it. C double bond out, that's that one. So I need a CH2SH. NCC, NCC. I'm going to have to send you a message in a minute to say, by the way, don't do questions 5A. What was the other one? Whatever the other one was. Don't do question 5A. D. The amino acids serine and aspartic acid are shown below. Serine, longest carbon chain, 1, 2, 3, so that's a propanoic acid. You've got, so that's propanoic acid there. You've got a hydroxy group there, and you've got an amino group there, so it's... Ooh, what takes priority? 2 amino... That's 2 amino and that's 3 hydroxy. I'm just not quite sure which one goes first. 2 amino, 3 hydroxy, 3 hydroxy, 2 amino. 2 amino, 3 hydroxy, propanoic acid. You've got an amino, there's propanoic acid, you've got a hydroxy group on one end and you've got an amino group in position 2. I think that's the way around. Draw the structure of the species formed when aspartic acid reacts with aqueous sodium hydroxide. Aspartic acid, NCC. I'm just going to draw it as it is first. H. CH2COOH. Right, so in aspartic acid, that is the NCC. They're drawing it up that way, just trying to be a bit clever, isn't it? So that's the side group. So anyway, if you have sodium hydroxide, this has got two acid groups. So if you add OH minuses to this, you'll get rid of that H plus and you'll get rid of that H plus. Draw the structure of the species form when serine reacts with dilute hydrochloric acid, so in other words, H pluses. Serine, NCC, double bond O. Well, they've drawn it like, they've drawn this one like that. There's the NCC there. Then you've got an H and a CH2OH. Alright, so what will happen if you throw H pluses at this? Well, I'll tell you what, they're going to stick on there. So you'll have another one there and you'll have a plus on there. Draw the structure of a species form when serine reacts with an excess of bromomethane. Bromomethane. What's serine then? Serine looks like this. So if you add bromomethane, oh, this is blooming quaternary amine salts. Quaternary amine. Jeez, I haven't done this for years. What you'll get, this is your serine, and you'll end up with a CH3 in each of these positions. Quaternary amine salts, I think they're called. I haven't taught that. I think last time I did that was in uni. Quaternary amine salts. Ask PL about that one. Draw the... oh, that was that one. Right. Next. At least I'm teaching the NCC thing. That's quite useful. Right. Consider the tripeptide shown below. Look. NCC, NCC, NCC. 3 amino acids. Name the process by which the tripeptide is split into the amino acids. Hydrolysis. Hydrolysis. Lysis means to split. Hydro means with water. Give the IUPAC name for the amino acid K. Alright. This amino acid would have had a C double bond O, OH. So it's at 1, 2, 3. Propanoic acid. And there's the propanoic acid bit. 2 amino propanoic acid. Yeah. Draw the structure of the zwitterion of amino acid. Alright, NCC. Double bond O. Right, the zwitterion then, you remove the H off that end and stick it onto this end. There's the zwitterion. Draw the structure of the species. M at low pH. Low pH means in acid conditions. NCC. Alright, I'm getting it right. Acid conditions, you end up with an H plus on this end. And this end stays acidic. H and then whatever group it's meant to be there. Consider the amino acid serine. Draw the structure of the product form when serine reacts with an excess of CH3Br. Right, what are you going to add? We've seen this just a minute ago. CH3, CH3, CH3 plus quaternary ammonium salts. Draw the structure of the dipeptide formed by 2 molecules of serine. NCC, NCC, double bond O, OH, double bond O, H, hydrogen there, hydrogen there, hydrogen there. All you've got to do is say, what's this? CH2OH, CH2OH, done. Q7. What questions did I ask you to do? I'll just have a look on here. I've been recording for 19 minutes, goodness me. Time flies when you're having fun. Question 1 to 10 and 12. Apart from aspartame. Aspartame has a sweet taste and used in soft drinks. Hydrolysis of aspartame forms methanol initially. After a long time, the peptide link breaks to form 3 amino acids. Neither of the amino acids taste sweet. Apart from the release of methanol, suggests why aspartame is not used to sweeten foods that to be cooked. I imagine that when you cook it, NCC, I imagine that breaks. You probably break the bond when you cook it. and therefore it won't taste sweet anymore because it won't be aspartame. That's my thoughts. Where's my mark scheme gone? Let's have a look what it says. Question 7. Forms non-sweet amino acids. It could speed up the breaking of these bonds, as though heating it will speed up the breaking of those bonds. Suppose I didn't really say that, did I? Give the IUPAC name for aspartic acid. Alright, we're getting used to these now. If you have a look here, aspartic acid, 1, 2, 3, 4 carbon chains. So it's butane dioic acid, 2 amino, 1, 2, 3, 4. 2 amino butane dioic acid. 2 amino butane dioic acid. When you've got a dioic acid, so this is 1, 2, 3, 4, 5. This is pentane dioic acid, not just. So if you had one, it'd be pentanoic. If you had another one, it's pentane. You put an E in the middle, dioic. Right. Draw the organic species formed by aspartic acid at high pH. NCC. High pH means OH minus. So you draw aspartic acid out, but you make sure you remove the H plus from this end. Draw the zwitterion of phenylalanine. Zwitterion, you make sure there's an O minus on this end, and there's an H plus on this end to fill the middle bit in. Pair of stereoisomers. Stereoisomers is same structural formula but a different arrangement of atoms in space. Explain how a pair of stereoisomers can be distinguished. They rotate plane polarized light in opposite directions. Question 8. Name and outline the mechanism for step 1. So you're going from an aldehyde, you're adding Cn minus to this. That is nucleophilic addition, I think. I don't do that one myself. That's nucleophilic addition. Yeah, cool. And you've got to know this mechanism yourself. I see if I can remember it. I do have the mark scheme up in the corner, but I'm going to try not to look at it. Right, so that's delta positive, that's delta negative. A Cn minus with its lone pair there, I'll go whoop whoop. That will kick electrons to there, so then you'll have CH3, CH2, C, O with a minus on, I think we always draw the lone pair on there, CN, H, and this picks up an H plus because it's done under acidic conditions. Done. And then you draw the final product. Give the IUPAC name of the product of step 2. Step 2, product, IUPAC name, carbons 1, 2, 3, 4. Oh, what's that then? Butane nitrile. That's butane with a C double bond O at the end. You've got C, 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 N. That's butane nitrile. What carbon is it on? 2-bromobutane nitrile. Step 3, give the reagents. Step 3, give the reagents and a necessary condition in the mechanism. Step 3, how do you turn bromo into NH2? Well, you're going to do nucleophilic substitution with NH3. You need an excess of NH3. Cool. Yeah, you need 2 lots of NH3 to do that. That's year 12 chemistry. At room temperature, the amino acid X exists as a solid. Oh, what's that question again? At room temperature, X exists as a solid. Alright, so that means, so if it's a solid, okay, I think what they're getting at here is, it's a small organic molecule and you wouldn't necessarily expect it to be a solid. It's a solid because it forms its zwitterion, which is that. So that's what you'd expect it to draw there. So you do your NCC with a double bond O minus. So this idea, solid at room temperature, it wants the zwitterion because this solid has got ionic bonds. Why is the melting point of this higher than this? Because this will have ionic bonds between neighbouring zwitterions and this will have hydrogen bonds. And ionic bonds are stronger than hydrogen bonds. There are many structural isomers. Oh, I'm nearly out of ink. Look at that. There are many structural isomers of X. Draw a structure of an isomer of X that is an ethyl ester. Huh? A structural isomer of X that is an ethyl ester. I think I'll draw the ester. I think I'll draw the ester group in here. Ethyl ester. Ink, don't fail me now. Ethyl ester. So I've used a CH3 and a CH2. So I've got a. There's me C. There's me COO. COO. There's me CH2. CH2. So I've got a CH. I think it's that. I can't even see what question I'm on now. What question is that? Cannot find it. Ethyl ester. What question am I on? Question 8. Oh, that's why I'm looking at the wrong one. Looking at question 9. Ethyl ester E. Oh, nuts. I've done too many of them, haven't I? CH. I think that's just an H. Yeah, I mucked that up. So I read that as being NH2 twice. Anyway. Draw a structural isomer of X that is an amide and also a tertiary alcohol. You know what? I can't be bothered. I've got to finish this video. My focus on this video is to get you through the. Should I do this? That's an amide. Right. I think I'd start off with the amide. That's the amide group, and also a tertiary alcohol. So a tertiary alcohol. I'll draw an alcohol in there, and then I'll go. No, I think I'll do my alcohol. I'll do a carbon, and then I'll do a carbon, a carbon. Maybe I'll do that. CH. There's my tertiary alcohol. 1, 2, 3. 1, 2, 3, 4. Did that work? I'll have a look, see if that's what it wants. Oh yeah. Oh, nailed it. Okay. Do you know what? I started off with the amide. I drew an amide link and then made the rest work. So anyway, not that great teaching that. You're seeing me sort of struggling my way through these, but at least you're seeing me doing them. I'm not practicing them. Practicing them. Draw a structural isomer of X that has an unbranched carbon chain. Oh, flipping heck. And can be polymerized. Oh, we haven't done polyamide. I'm leaving it. Draw the structure of the tertiary amine formed then. When X. I need to find X now. When X reacts with bromomethane. Tertiary amine. So you're going to have CH3 on there. That's a tertiary amine, not the quaternary ammonium salt. The tertiary amine. So you'd have two CH3 groups on there. I don't know if you've done tertiary amines and quaternary ammonium salts. I don't know yet. Question 9. NCC. This is a tripeptide. Draw a separate circle around each of the asymmetric carbon atoms. So I'm looking for any carbons that are bonded to 4 different groups. This carbon is bonded to 1, 2, 3, 4 different groups. That's you. You're one of them. Let's have a little look. This carbon is bonded to C. But that's it. Eh? This carbon is bonded to that, and that. That's not. That's bonded to 1, 2, 3, 4 different groups. I think that's it. 1 mark for that. Zwitterion of alanine. Alright, so, you know, yeah, you see me not really go through all of the questions, but I hope you're getting the idea of zwitterion is like they're a piece of cake. Alanine, you make sure you've got alanine there. Alanine's got a CH3 in that position. That's alanine. The zwitterion of alanine. Remove the H plus and put it over this end. Give the IUPAC name of threonine. Threonine. 1, 2, 3, 4 carbons, so it's bute. It's going to be a butanoic acid. Right, there's butanoic acid. It's going to have an amine in position 2, 2 amino, 3 hydroxy butanoic acid. 2 amino, 3 hydroxy butanoic acid. Yeah. There's the group. You've got an amine in position 2 and you've got a hydroxy in position 3. 2 amino, 3 hydroxy. Give the species formed by lysine at low pH. Low pH is acid. Lysine, you go NCC. If you're in acid, this end becomes acidified and this end stays in acid, and then you draw the group in there. The repeating unit, right, name this. The repeating unit shown as a polyester, name the type of polymer. Well, you can't say polyester, so condensation polymer. I don't know if you've done them yet. It does say the mark scheme says allow polyester. The repeating unit shows a polyester. What type of polymer is it? A polyester. Right. But it's condensation polymer or polyester. Name the AUPAC name for the. Give the AUPAC name for the alcohol used to prepare this polyester. The alcohol. You can tell the alcohol would have been this one. 1, 2, 3. It's propane diol. 1,3-diol. I don't know if you've done polyesters, you get what I'm talking about, but I'm not teaching you polyesters in this one. Repeating unit again. It's not a name the type of polymerization. By the way, the type of polymerization is addition polymerization, but you haven't done addition polymerization. Maybe draw the structure of each alkene monomer. If you're looking at this going, you don't know how to do this, that's fine. I'm just sort of showing you that it's fine. I'm not having to get me textbooks out, like it's quite straightforward. You can see that and that come from 2 alkenes joined together. One of the 3 compounds shown in part A, B and C cannot be broken down by hydrolysis. Don't know, can't bother looking at that. Sorry guys, I'm going to focus on the fact that I taught you about NCC. NCC. It's Viterion formed by alanine. N, C, double bond O. It's Viterion O minus plus H, NH2. Draw the structure of the compound forming alanine reacts with methanol in a presence of a small amount of concentrated sulfuric acid. So this is alanine. It's got a carboxylic acid group. When carboxylic acids react with alcohols, you make esters. So you go NCC, double bond O, methanol. CH3, you fill in the rest of that. If you do it in acid, will that be acidified? Yeah, it might be. The examiner says you can have it as acidified or not. I don't know if you've done esterification yet, so you form an ester. Alanine, NH2 in that position. Aspartic acid at high pH. High pH, that's OH minuses, so you'll get rid of the acid group, aspartic acid. Draw the structure of a dipeptide from 2 aspartic acids. Go NCC, double bond O, OH, double bond O, H. See, that's all without the thinking, and then you just got to pour the aspartic acid thing here. NH3, no, NH2, piece of cake. Is that it? Oh, and then let's take the question 12. I don't know why I missed out question 11. Question 11's fine and all. AUPAC name of that, 1, 2, 3. Well, there's quite a lot of carbons in there, longest carbon chain. Good that. Lysine reacts, so that's in H+. This is in OH-. This is methanol, so this is going to make an ester. The mass spectrum gives a major peak at this. I don't know about that. Draw a dipeptide, NCC. The dipeptide acid conditions. Yeah, you haven't done column chromatography, but it suggests if lysine leaves a column after alanine, it means lysine was more attracted to the column. It's formed stronger attractions to it. Anyway. 12. Name the type of protein structure. That is an alpha helix. Yay, biologists celebrate. Alright. Explain the origin of the interaction represented by the dotted lines in the figure above. The origin of that, right, it's a hydrogen bond. The hydrogen bond occurs because there is a large electronegativity difference between the N and the H. The large electronegativity, come on, Norton. A large electronegativity difference between the N and the H, that's 1 mark. This means that the H is strongly delta positive, 2nd mark. This is attracted to a lone pair on in this case, a C double bond out. A lone pair on an oxygen of a neighbouring C double bond out. See what the mark scheme says. Can you see I'm lacking motivation? I'm just saying I'll get 4 marks. Oh, you know what? I said alpha helix, but you have to actually say secondary. Whoops. But it is an alpha helix. Wonder if you'd have got the mark for that. There are 2 types of secondary structure, alpha helix and beta pleated sheet. I was being a bit too specific, maybe. Right. So it's gone with... See, I've drawn on here the polarities of these. So it says you need to mention somewhere that these are polar. I think I've done that. They said that the nitrogen and the oxygen are both very electronegative. I only said the nitrogen and hydrogen are a big electronegativity difference. I think I'm having that mark. I'm not sure. Hydrogen bond between the O and the H, which I've drawn. A lone pair of electrons on the oxygen atom is strongly attracted to the delta H. Yeah, right. The mark scheme that you've got is very sort of prescriptive. I think my answer was fine. There's a large electronegativity difference between the N and the H, making the H very delta negative. So I think that covers that. I then mentioned that a neighbouring oxygen lone pair is attracted to the delta positive H, which I'm happy with. I then drew delta negative and delta positive on there, which I'm happy with. I think I'm scoring 4 marks on that. 37 minutes of listening to me waffle on. Cool. Bye.